So now you can already start seeing why periodic orbits might be useful. Because specifying all possible trajectories is like specifying all normal numbers. It can be done by infinite sequences. But we're not interested in everything to infinite precision. We're just interested in sufficient resolution in a state space. We're just interested in things that have certain future and certain path. And it turns out every one of those owns a periodic point in it. So if I know all the periodic point of certain length, I will know all representatives of all the regions of trajectory of certain length. And in other contexts, we call this shadowing, saying that in every region, they are all qualitatively similar orbits, and there is periodic orbit that shadows them up to resolution of that region. So what is a periodic? So what's, for example, a fixed point? You know it very well just by looking at a billiard. If I'm so clever that I go at 90 degrees here between the centers of two of these guys with infinite precision, I'll have an orbit that'll go back and forth forever. So according to this symbolic dynamics, in the future, this orbit will look like 0, 0, 0, 0, 0. But I know also what it did in the past. It's always been there, so it looked like 0, 0, 0, 0. And we will use notation that infinite repetition of some symbol block, I can denote it as a bar. So this is same. So there's thing about periodic points and periodic orbits, but we know that every point on this bouncing trajectory belongs to this symbol sequence, 0 infinite many times. Or there will be a simple sequence where I go here, I hit the next and I just come back and I keep going. According to this rule, that will say that our and all the business does the same thing in the past, and if you keep trying. In this particular system, we have two scripts, qualitatively, the two fixed points that characterize the scripts. And they characterize both the past and the future. So there is a point here, you see it for all times, and there's a point here that's here for all times. And for example, this one sits on the equal 0, but the other one doesn't because it's final error. Now, what about this orbit here? Do I have a representative for it? This is the orbit where I bounce back, I bounce forward, I bounce. It will have a property. I'll start bouncing back, then I'll bounce forward, bounce back, bounce forward, bounce back, bounce forward. Now the demand of the path is the same. And that will be periodic orbit 1, 0. And you'll have two cycle points. If this is now, then one of them will look like I'm at 1, and in the future I repeat it forever. I can put a point here if I want to increment many times, and I just call it 0, 1, 0, 1. But the other one looks like orbit 0, 1 is the set of points. Remember, there will be a real point in a physical space, periodic orbit which will have its append array 1, 0, and then be another one, which will be called 0, 1. This thing does it will hop between here and there. You know, that might be x 0, 1, and that might be cycle points of permutation. So now you see, I have a method to this partition. This will be very helpful for us because this partition will enable us to find smaller and smaller regions. And remember how we did it physically. Physically, these lines were you looked at the edges of the domains and iterated. And that once you have these domains, then you can always find the periodic orbit in them. You can always find represented error. Automatic machinery becomes just from topology of this topology, which is very obvious when you look at a Poincare section, and totally non-obvious when you start looking at this, because this might look something like that. So very soon you can, but in Poincare section, it's beautiful, and it's organized when you look at it. These lines have to do with unstable and stable manifolds. So they have a good geometrical invariant we already have. And you have a machinery that enables you to find as many periodic orbits as you can. So for various forms like this, sometimes people can remember the record. You know, it's on a computer, but maybe the record is of order of 500 million periodic orbits. You can run a computer. Now, the theory that we'll develop here, you'll find out that maybe 5 of these periodic orbits give me very good predictions for what I'm trying to compute. Or maybe 100 or something, but you know, there'll never be billions of them.